You are now.
Good afternoon. Last time we didn't finish, and today I would like to continue exercises from the previous classes. So we can start with task number 16 from this previous PDF. So we have to compute inverse matrices using the Gauss-Jordan method. So first, what are inverse matrices? So if we inverse matrix is defined, so if we have matrix called A, we can try to find inverse matrix, and if we multiply a square matrix A, so A has to be in the set of n by n matrices, and if we multiply A by its inverse matrix, which we denote like this, we should obtain the identity matrix. And it should also work in the other direction. So A inverse time A should be also the identity matrix. And how we can compute a matrix, how can we compute an inverse matrix? So from we can see that if we multiply A by its inverse and we obtain identity matrix, we can write it like this. So I think that it would be good to start with 3 by 3 for 3 by 3 matrices. So if A is a 3 by 3 matrix, then after multiplication by its inverse, we should obtain the identity matrix. So we can write that we multiply A by its inverse, and then we can denote each column of this inverse matrix. So this A1 inverse, it's only this is the variable that we used to call this first column of matrix A. And similarly, we can use similar notations for the other two columns. And we know that from the previous classes, you can, I hope that you remember that that each column of the resulting matrix, when you multiply matrix by matrix, is a combination of columns of this left-hand side matrix, and coefficients of these linear combinations are in respective columns of this right-hand side matrix. So it means that we can write that the first column is of this, or maybe I think that it would be better to write it below these two matrices. So this product of these two matrices can be written like this, that the first column is A multiplied by A1 inverse. The second column is A by A2 inverse. And the third column is A by A3 inverse. Okay, so it should be here, and it should be equal to this identity matrix. So it means that if we want to find these three columns, which are the columns of the inverse matrix, we just need to solve three systems of linear equations. It is because A by A1 inverse should be equal to 1, 0, 0. A by A2 inverse should be equal to the second column of the identity matrix, and A by A3 inverse should be equal to 0, 0, 1. So if we want to find the inverse matrix of A, we just need, then we know A and we know these columns of identity matrix. So the unknowns are only these three columns, these three vectors, A1 inverse, A2 inverse, and A3 inverse. So we just need to solve these three systems of equations. And actually, the last task that we did last time was about simultaneous solving of systems of equations that have the same matrices for each system. Okay, so you can try to remind to yourself how what this task, and we can use a similar way to solve this system of equations. So it's called Gauss-Jordan method, and we start with augmented matrix, and instead of appending just one additional column, we need to append all columns of this inverse matrix, and then instead of this, maybe I can write it in more general way. So we just append the whole identity matrix, and we need to do these row operations to obtain identity matrix on the left side, and then we can find the columns of the inverse matrix on the right hand side. So we can do, maybe I will try with this third example in task number 16. So I will try to compute the inverse matrix of matrix A, which is 1, 1, 1, 1, 2, 2, and 1, 2, 3. Okay, and so first I can start to write this augmented matrix. Okay, and then we can do these row operations. So we have 1, 0, 0, 1, 1, 1, 1, 0, 0. And first I use this pivot element, in order to eliminate this entry below it. So I need to subtract the first row from the second. So it will be 1 minus 1 is 0, 2 minus 1, 2 minus 1 is 1, 2 minus 1 is 1, 0 minus 1 is minus 1, 1 minus 0 is 1, and 0 minus 0 is 0. And I can also eliminate this entry, so I also need to subtract the first row from the third one, so it will be 0, 1, 2, negative 1, 0, and 1. Now the next pivot will be this 2, 2 element, so I can rewrite these first two rows, 0, 1, 1, and I will also subtract the second row from the third row, so it will be 0, 0, 1, negative 1 minus negative 1 is 0. Okay, and then we have negative 1 and 1, I think. Okay, so we have the first stage. The first stage is completed, and now we have to do elimination upwards. So we use this pivot to eliminate these two ones above it. So it will be 0, 0, 1, 0, negative 1, 1. Then we have to subtract the third row from the second row, so it will be 1, 0, 1, 0, negative 1, 2, and negative 1. And we need also to subtract the third row from the first row, so it will be 0 here. Then we have 1 plus 1 and negative 1. And the last thing we need to do is to subtract the second row from the first row. So 0, 0, 1, 0, negative 1, 1. Then we have 0, 1, 0. Okay. And the first row is just to 1, 0, 0, and I am subtracting the second row from the first row. So then we have 1 minus negative 1 is 2. Then we have 1 minus 2 is negative 1, and here there should be 0. Okay, so yes, I cannot write here, but we can finally read these entries of the inverse of A. So the first row is 2, minus 1, 0, minus 1, 2, minus 1, and 0, minus 1, and 1. Okay, so we can check now if we have to check if we multiply A by A inverse, if we actually obtain this identity matrix. Okay, so let's do it. So the first we need to multiply. So I want to multiply A by A inverse, and I think that I can write the result here. So first we can multiply first row by first column. So we have 1 times 2 plus 1 minus 2. So we have 1 here. Then we can multiply the second row by the first column. So it's 2 minus 2 is 0. Then we have 2 minus 2 plus 0 is 0. Then first row times the second column. So it's minus 1 plus 2 minus 1. So it's also 0. Then we have minus 1 plus 4, which is 3. minus let me do it again. Minus 2. So yes, it's 3 minus 2 is 1, and minus 1 plus 4 minus 3 is 0. Then the first row times the third column is 0. Negative 1 plus 1 is 0. 0 minus 2 plus 2 is 0. And finally, the third row times the third column. So it's 0 minus 2 plus 3 is 1. Yes, so it seems to be correct. We multiplied A by A inverse, and we obtained the identity matrix. Yes, and then you have two other examples in this task number 16. So I encourage you to do it later by yourself. And now I would like to move to the next topic, but maybe I will provide you more information about inverse matrices. So first of all, inverse matrix can be only for square matrices, but not for all square matrices. So there are matrices that for which you cannot find inverse matrix. For example, if you have 1, 1, 1, 2, 2, 2, and let's say 1, 1, 1, and then we can so if you start doing elimination, you will make these rows 1, 1, 1, and there will be all zeros below this first row, and but there will be not zeros on this right hand side, so it will be not possible to solve this in this case. So there are invertible matrices that for which you can find inverse matrix, and there are also non-invertible matrices, and for these matrices you cannot compute inverse matrix, and this is similar to multiplication of numbers. So if you that there is one number for which you cannot find its inverse, it's 0. But in the case of matrices, you need to look at determinant, and we will talk about it later. But all matrices that have determinant equal to 0 are not invertible. Yes, and so we can not all square matrices have inverse, and for 2 by 2 matrix there is an easy formula to find its inverse. So if we have 2 by 2 matrix which has these elements A, B, C, D, and we want to find its inverse, you can try to remember that so first you have to divide 1 by determinant of this matrix. So for 2 by 2 matrix, this formula is you need to multiply elements of that are on diagonal of this matrix, and then you have subtract product of diagonal entries, and then you have to multiply it by, so on diagonal you need to change the order of these two elements, and you need also to change signs of diagonal elements. So here we have minus b and minus c. So yes, you can. So that's an easy formula that we will use it a lot later. And the last, so you can see that if we have ax is equal b, so that's how now we can write systems of linear equations, and you can multiply both sides by inverse of a. So then, but you need to, as multiplication of matrices is not commutative, so you need to be careful, and if you multiply left-hand side, so if you put this A inverse in front of the left side, you need also to put an A inverse in front of the right-hand side, or you can multiply both sides from the right. But in this case, it would be even not possible because of these dimensions of these matrices. So then you have A inverse times A is identity times X is A inverse times B. So identity times X is just X. So if you want to, so you can solve a system of linear equations by Ax is equal to B by multiplying B by A inverse, and then you will obtain vector X with values of unknowns of this, with values of the unknowns of this system. Okay. I think that now we can start with the next set of exercises that I have uploaded today. So it's about LU decomposition. So first, okay. First, we can start with this task number 1. So forward elimination changes system of linear equations, which we can write as 1, 1, 2 times x is b. And after elimination, I mean downward elimination, we need just to eliminate this entry. So if we subtract this first row from the second one, then in the second row we will obtain 0 and 1, and we need also to subtract the first element of b from the second one, and then we obtain just a new vector which is called c here. And let's read what we have to do with this. So write corresponding systems, original and triangular, for B5, 7. Okay, so then we have 1, 1, 1, 2 times x is 5, 7. So if we, so x is a vector here, okay, and we have to similarly to this left-hand side, we need to subtract the first row of this matrix from the second one, and we need also to subtract first element from the second one. So then we will obtain 7 minus 5 is 2. Okay, and then we can, of course, solve this system using back substitution, but let me write the rest of this task. So that step subtracted L21 which is a number by which we multiplied the first row and subtracted from the second row. So we had to just multiply the first row by 1, and then we need to subtract it. So L21 is equal to 1 in this case. So this is the number that we had, that we used to multiply the first row before subtracting it. And then the matrix for that reverse step is L. Okay, so then the reverse step adds L21 times row 1 to row 2. So you can see that if we add this first row to the second one, so 1 plus 0 is 1, 1 plus 1 is 2, and 5 plus 2 is 7. So that's the reverse step. And the matrix for that reverse step is L, and we can write this matrix. So if we use this row, it won't change the first row of the multiplied matrix, and then we can write these numbers, and we can call this matrix as U, because it's upper triangular, so all numbers, all entries below main diagonal are 0. All entries below, and all entries above the lower, so that's why it is called L, because it's lower triangular matrix. So for lower triangular matrix, all entries above main diagonal are zeros. So if we multiply by L this second system of linear equations, so we know that this matrix can be called U. If we do this multiplication, then we obtain LUX is equal LC, and this is the same, LC, this is the same as AX is equal to B. And yes, I will try to back to this you the composition later, so you can treat it as an introduction to this LU decomposition, and I will try to explain it in more detailed way. And before we can try to do this task number 2, because I think that it maybe it'll be easier to explain this LU decomposition after doing this task number 2. So we have to write down 3x3 matrices that produce elimination steps. So in this first in the first example, we have to write a matrix called E21 that subtracts row 1 multiplied by 5, actually 5 times row 1, and we have to subtract it from the row row 2. Okay. So how can we build such a matrix? Do you know how to construct such a matrix? Do you have idea how to write E21? If not, maybe it will be good to explain or just to remind how these linear combinations of rows are performed during multiplication of matrices, but maybe you will be already able to provide me the answer for how this E21 matrix should look like. If you know, please write it in the chat. Okay, no answers, so I will try to go back to this multiplication of matrices. So if we would like to multiply matrix, let's say 1, 2, 3 by 1, 0, 1, 2, 3, let's say -2, 1, 2, 2. Okay, so what will be the dimensions of the resulting matrix? So here we have matrix which has dimensions A times 3, and then we have 3 times 3. Okay, so these two dimensions are the same, so it means that this operation is allowed, and the resulting matrix will be also A by 3. So we will obtain a row. Okay, and during the previous classes, I told that the resulting matrix contains each row of the resulting matrix. So in this case, the resulting matrix has only one row, is a linear combination of rows of this right-hand matrix, so of this second matrix in the product of the left-hand side, and coefficients of these linear combinations are in the rows of the left matrix, of this first matrix. So this row will be, we can write that it will be 1 by the first row plus 2 by the second row plus 3 by the third row. Okay, so we can write that it will be 1 times the first row, 0, 1, plus second element, so it will be 2 plus 2, 3 minus 2, plus 3 times 1, 2, 2. Okay. So if we add these three vectors multiplied by numbers, we will obtain 1. Maybe I will multiply by these numbers only. So it will be 1, 0, 1 plus 4, 6, negative 4 plus 3, 6, 6. And then we have to add these three vectors. So 1 plus 4 plus is 5 plus 3 is 8. Then we have 0 plus 6, which is 12. And 1 minus 4 is negative 3 plus 6 is 3. Okay, so this is how we can find this linear combination during this multiplication. Okay, so that's the result. And how about multiplication of 2 by, we can do another example where we have to multiply 2 by 3 matrix by 3 by 3 matrix. So now these two dimensions are the same, so the resulting matrix will be 2 by 3. And let's I will give you some numbers here. Negative 1, 2, 2, 3. Okay. So in this case, in the resulting matrix, we will have 2 rows, and in the first row will be a linear combination of these 3 rows, but with these 3 coefficients. So it will be 1 times 1, 0, 1 plus 0 multiplied by 2, 1, negative 1 plus the third entry in the first row, which is 2, by the third row of this second matrix. So it will be 2, 2, 3. And in the second row, we will have a linear combination of the same rows, but this time we will use different coefficients. We will use the coefficients from the second row of this first matrix. So 3, 1, 1. So we have to multiply the first row by 3, the second row by 1, and the third row also by 1. So finally, we'll have 1 times 1 plus 0 plus 4, which is 5. 1 plus 1 times, so it will be 0 plus 4, and 1 plus 0 plus 1 plus 0 plus 6, which is 7. And the second row will be 3 plus 2 plus 2. So it will be 7. 0 plus 1 plus 2, which is 3. 3 minus 1, which is 2, plus 3 is 5. Okay, so that's the result. So if we want now, we can back to this task. And now we have to construct a matrix in which we have to multiply the first row by 5 and then to subtract it from row number 2. So in this case, we can start with writing. So after this operation, after subtraction from the row number 2, the only row that will be modified is the row number 2. So the first row won't change, and so we can easily find these numbers in the first row of e to 1. So let's say 1, 0, 0, okay? Because if we multiply 1, 0, 0 by, we can it means that in the first row of the resulting matrix will be 1 times the first row plus 0 times the second row plus 0 times the first row. So finally it will be 1, 2, 3. Then we have to subtract the first row multiplied by 5. So in this second row, we have to place -5 here, 1 and 0. So it means that the second row will be -5 times 1, 2, 3 plus 1 times 4, 5, 6 plus 0. So this is the same as subtraction of the first row multiplied by 5 from the second one, and the last row has to be 0, 0, 1. Yes, so Marcin already wrote the good answers. So it will be like identity matrix with -5 in the second row, column 1. Yes, so finally we have to write it like this. Yes, so I actually should write it here. Yeah, so that's how we can construct this E21 matrix. I tried to explain it slowly, maybe too slowly. So let's try this second example. So how should we write this E32 matrix? So the matrix that subtracts -7 times row 2 from row 3. So please write it in the chat if you know the answer. Yes, so Marcin knows the answer, and let's wait for it. Okay, more people. Yes, so yes. Yes, exactly. So the answer here will be E3, 2. It's 1, 0, 0, 0, 1, 0, because these first two rows will be unchanged. So we just need to write rows like from identity matrix, and the third row has to be changed, and we can write it like this because we want to subtract -7 times row 2. So this is the same as multiplication of the row 2 by 7 and then adding it to row number 3. So this is how E32 matrix looks. And how about this third example where we have to write matrix P which exchanges rows 1 and 2. So do you have ideas how to write this kind of matrix? So in the first row, we should have the second row. In the second row, we have yes. So that's correct. So we have just to write 0, 1, 0 because we want just the second row multiplied by 1. We want to have it in the first row. Then we want to have the first row in the second row. And finally, we can leave the third row unchanged. So this is permutation matrix. Okay. So maybe one more. Maybe I would like to give you some comments about these permutation matrices. So if we have, let's say, a vector 1, 2, 3, and now if we multiply p times x, then we obtain, then the first and the second row will be exchanged. So we will obtain 2, 1, 3. So we just exchanged two elements. If we multiply P times matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, then, as we discussed earlier, we will exchange these two rows, the first and the second row. So the result will be 4, 5, 6, 1, 2, 3, 7, 8, 9. And how about multiplication from the right side? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. But now we will multiply it by p from the right side. So in this case, instead of exchanging rows, we will exchange columns. So the result will be, the first column will be the second column of this matrix. So I need to write 2, 5, 8. Then the first column, so 1, 4, 7. And the last column will be unchanged. So 3, 6, 9. Yes, so please try to remember that if you multiply from the left side, then you exchange rows, while if you multiply from the right side, then you need to exchange columns of the multiplied matrix. Yeah, and then we have exercise number 3 to multiply these E and F matrices. So we have E matrix, which is 1, 0, 0, A, 1, 0, B, 0, 1, and F is 1, 1, 1, and C below the second element. Okay, and you have, as you can see, there are many zero entries in these matrices, so you can try to compute it, to use that fact. So first we have to find E squared matrix, so E times E, so it will be 1, 0, 0, A, 1, 0, B, 0, 1, times 1, 0, 0, A, 1, 0, B, 0, 1. Okay, so, okay, and we can use the fact that we have 1, 0, 0, so it means 1, 0, 0 in the first matrix, so it means that it won't change the first row of the second matrix, so we just can write 1, 0, 0. You can see also that you have 0, 0, 1. So it means that the last column of this matrix is a linear combination of these three columns. So with coefficients in this column. So we have to multiply first column by 0 plus second column by 0 plus the third column by 3. So we can write 0, 0, 1. We have also 0, 1, 0, so it will be easy to write the second column, and as we have 0, 1, 0, so it means that the second column of the resulting matrix will be the second column of this first multiplied matrices. So 0, 1, 0, and we have these two elements, so we can, for example, multiply it using by computing dot products between rows and columns. So if we want to compute to one element, we need to find this dot product between the second row and the first row of this second matrix. So it will be A plus 0. So we can write 2A here. And then we have this element, so the third row by the first first column, so it will be B plus 0 plus B. So we need to write 2B here. Okay. Yes, we have. I missed the first two matrices that we have also to compute. So let me back there, and so we have to multiply E by F and then F by E. So E times F is 1, 0, 0, A 1, 0, B 0, 1, multiplied by F, which is 1, 0, 0, 0, 1, 0, 0, C 1. So we have this 1, 0, 0, so it means that we can write the first column of the second matrix. Yeah, and then we can use this 1, 0, these columns with zeros and ones. So the first column of the resulting matrix will be the first column of the left matrix. So 1A, B, because we need to multiply first column by 1, the second by 0, and the third by 0. Then we have 0, 0, 1, so it means that we can rewrite the third column of this matrix. So 0, 0, 1. And then we can calculate dot product of the second row on the second column. So it will be 0 plus 1 plus 0. So 1 should be here, and third row by the second column. So it's 0 plus 0 plus C. Okay, so in this case, you can notice that we have these two matrices, E and F. We can say that they are both lower triangular matrix because all elements above the main diagonal are zeros. And you can see that in this case, you can just rewrite these elements below main diagonal at their positions. Okay, so we have A at this position, B at this position, and C in this position. And but if we try to do the second of this product, so if we change order, so instead of calculating EF, we will calculate FE. So now I would like to compute the product of FE. So it's 1, 0, 0, 0, 1, 0, 0, C, 1. And then E. So it's 1, 0, 0, A, 1, 0, and B, 0, 1. So as we have 1, 0, 0, we can rewrite this first row. Then we have 0, 1, 0, so it means that I can also rewrite the second row of the second matrix. So it is A1, 0. Now I can use the fact that we have 0, 1, 0, so it means that I can rewrite the second column. So we have 0, 1, C. 0, 0, 1, it means that I should rewrite the third column at the third in the third column of the resulting matrix, so it will be 0, 0, 1. And finally, we have to multiply third row by the first column, so it's 0 plus CA plus, am I right? CA plus B, okay? Zero plus CA plus B. Okay, so in this case, it is not possible to, so it is not so easy as in this, as in this previous case, where we have just to rewrite these entries at their positions. So it depends on the order of these multiplied matrices. So if you have let's say in good order, so in the second matrix you have these elements below in the second column and so on, then it's then you can just rewrite these numbers. But in the opposite case, so when you have in the first matrix, you have elements under diagonal in the second column, and then in first, you cannot do it like this. And I think that it will be good if you will try to do after the classes by yourself this exercise number 4. So please think and try to explain why this product is correct. So in this fourth task, you have to you can see this you can see this product of three matrices, and you can easily find this product just by rewriting these entries under main diagonal at their positions. Okay, and please try to think why is that, and try to explain it with your own words. And I think that now we can try to. I will try to explain you this LU decomposition. So the goal of LU decomposition is to factorize A matrix into two matrices, L, which is lower triangular matrix, and U, which is an upper triangular matrix. Okay. And I will show you two ways how to decompose a matrix into product of these two matrices. So the first one is uses this elimination matrix that we discussed earlier today. So I think it would be good to have some examples. So we can start with this first example of exercise number 6. So we have this matrix A, 1, 2, 1, 3, 5, 5, 2. Okay, so yes, first we can find the matrix which will eliminate this entry. So we have to use this entry as a pivot, and we have to eliminate this 3. We'll do it by multiplication the first row by 3 and then subtracting it from the second row. So we can write that we have matrix, 3 by 3 matrix, which will do it for us. So I will rewrite this matrix A here. 3, 5, 5, -2, -5, -2. And so after this first step, the first row will be unchanged. So as we discussed earlier, we just need to write 1, 0, 0. Then in the second row, we will have the result of subtraction of row 1 multiplied by 3 from the second row. So what numbers I should write here in the second row? Can you write it in the chat? No, I have to multiply the first row by 3 and then subtract it from the second row. So at least the number 3 should occur somewhere here. So if I would like to to subtract the first row from the second row, then I would write -3, 1, 0. Okay, it's because I want to multiply the first row by -3, then add it to the second row, and I don't want to use the third row. Okay. Yes, is that okay now? So, and then I'd like to leave the third row of this matrix as it is. So I have to write 0, 0, 1. And then if we multiply these two matrices, then I have 1, 0, 0. So it means that I have to rewrite this first row. Then we have -3 plus 3 is 0. -6 plus 5 is -1. -3 plus 0 is -3. Okay. I probably -3 plus 5. Okay, is 2. And then I want to leave to rewrite this third row of the second matrix unchanged. So it's -2, -5. Okay, can you understand it now, or should I explain it in a more detailed way? So let's try with the next step. So in the next step, I will use this matrix as a starting point. So I will rewrite it here. So it's 1, 2, 1, 0, -1, 2, -2, -5, -2. And now I would like to eliminate this number. So I need to find entries for this matrix to find this result. So in this case, if I want to eliminate this -2 in the third row, I need to multiply the first row by 2 and add it to the third row. So only third row will change, so I can write rows that are rows of the identity matrix, and in the third row, as I said earlier, we want to multiply the first row by 2 and add it to the third row. So what numbers should be in the third row of this matrix? Okay. You earlier you provide me. Mm-hmm, 201. Yes, great. 201. So after this step, the first two rows will be the same, and then I multiply the third row by the third row by the first column, so it's 2 plus 0 plus -2, so it's 0. Then I have 4 plus 0 minus 5, so 4 minus 5 is -1, and then we have 2 plus 0. Let me do it again. 2 plus 0 minus 2, so 2 minus 2 is 0. And finally, I will use this entry as a pivot, and I want to to eliminate this -1 below it. So I will try to use this space here. So now I will have this empty matrix, and I will use this matrix as a starting point. So it will be 1, 2, 1, 0, -1, 2, 0, -1, 0. So in this case, I have to multiply the second row by -1, and then I have to add it to the first, to the third. I have to add it to the third row. So I can write 1, 0, 0, 0, 1, 0, and what should be written in the third row? Okay, can you write it in the chat? Okay. Yes, so it's 0. Yeah, that answer is correct. So it's 0, -1, and 1. We have 1, 2, 1. Then the second row we need also to rewrite here. So it's 0, -1, and 2. And finally it's 0, 0, and so if we multiply the third row by the second column, it's 0 plus 1 minus 1, which is finally 0. And if we multiply the third row by the third column, then we have 0, -2 plus 0. So I think that we should write -2 here. 0 minus 2 plus 0. Yes, so that's the upper triangular matrix that we obtained using by performing these Gauss elimination steps. But this time we wrote these elimination steps using matrix notation, and we can we have this E21 matrix. We can call this matrix as E21 because we multiply, because we want to eliminate matrix in the second row and the first column, and we multiply it by A. And this gives us E21 multiplied by A. In this row, we start with this matrix E21 multiplied by A, and we multiply it by matrix that we can call E31, because it has to eliminate this element in the third column, in the third row in the first column, and it also has non-zero element at this in this 3-1 position. So after that we have E31 multiplied by E21 multiplied by A. Okay, and finally we have to use to eliminate 3-2 elements. So this matrix will be called E32 multiplied by, and this matrix we can call it is the same as that one. So it's E31 multiplied by E21 by A. So we can write that E32 by E31 by E multiplied by E21 multiplied by A is the same as upper triangular matrix. Now we have to, but our goal here is to find how we can write A as LU. So we can multiply this matrix by this equation by inverse of this whole expression. And yes, another important thing to remember is that if we want to find an inverse of multiplication of two matrices, let's say AB, we can write it as a product of inverse matrix, but we need to change their orders. So it will be B inverse times A inverse. So if we would like to, so now we can multiply this expression. I would like to write it maybe again to be able to no, it's E32. E32 by E31 by E21 multiplied by A is U. And as matrix multiplication is associative, we can write, we can place this parenthesis here, and we can try to multiply both sides by inverse of this expression in parentheses. So it will be E32, E31, E21 inverse. And if I multiply inverse by this whole expression, it finally leads to identity matrix. So on the left side, I will end with this A matrix, and at the right-hand side, we have to multiply U by this expression. So it's E32 multiplied by E31 by E21 inverse by U. And as I earlier mentioned, we can change order and write this that way. So it's E21, E31 inverse, E32 inverse multiplied by U. And I think that it will be clear that that this product will be a lower triangular matrix, so all we need to do is just to multiply these inverses of elimination matrices, and this is how we will end with this matrix L. So yes, so now we have to use this E21, E31, and E32, so these three elimination matrices. So E21 E31 is 1, 1. So all elimination matrices have ones on their diagonals and 0 above diagonals, but there is only one non-zero element below diagonal. So in the case of E31, we need to place 2, and E32, we have also once on main diagonal, and it was -1 as I remember, as far as I remember. Yes. So now we know that matrix L is E21 inverse multiplied by E31 inverse multiplied by E32 inverse. And first of all, it is relatively easy to find these inverse matrices of elimination matrices, because we've already mentioned today that you can, if this matrix do the following, that it subtracts the first row from the second row. It subtracts the first row multiplied by 3 from the second row. So if we want to do the reverse operation, we need to add this first row multiplied by 3 to the second row. So in the forward operation, we subtract first row multiplied by 3. In the reverse operation, we need to add this row multiplied by 3. So if we want to find inverse of E21, we just need to change sign of this entry. So instead of -3, it should be just 3. Now, similarly, we can do with inverse of E31. And E32. Okay, so now we have all these three inverse matrices, so we can write that L is, we need to start with this E21, so it's 1, 1, 1, 3, 0, 0, 0, 0, 0. This is multiplied by E31 inverse, so it's 1, 0, -2, 0, 0, 1, and 1, 1, 1, 0, 0, 1, 0, 0, 0. And we have already had today these examples where we multiplied lower triangular matrices And we have this example that these non-zero entries below the main diagonal are in the correct order. So, and this is what's the case in always when we try to find this LU decomposition, that we can just rewrite these elements, these non-zero elements below the main diagonal at their positions. So we just need to write 3 here, -2 should be here, and 1 should be here. And finally, we have this we have this L matrix. So now we can try to write the whole decomposition. So matrix A is 1 to 1, 1 to 1, 3, 5, 5, and -2, -5, -2, and this is L by U, 1 to 1. We know that L matrix is like this. So we have 3, -2, and 1. And upper triangular matrix has the following numbers. Yeah, we can use so -2 to -2, -1 to. Okay, and now we can check if we multiply these two matrices, if we would end with this result. So please check it later. And I think that we continue with this subject next time. So if you have any questions, I'll be happy to try to answer it. And if not, thank you for your attention and see you next week.